Good afternoon, everyone. Welcome to our virtual informal systems seminar this week. And it's my great pleasure to introduce to you our speaker today, Jr-Shin Li, Professor Jr-Shin Li. Professor Jr-Shin Li is a professor of system science and mathematics in the Department of Electrical and System Engineering at Washington University in St. Louis, where he also holds a joint appointment in the Division of Biology and Biomedical Sciences since he joined the university in 2006. Professor Li received his bachelor and master degrees in science from National Taiwan University and a PhD degree in applied mathematics from Harvard University in 2006. His research interests lie in the area of systems, computational and data sciences, and their applications to a wide range of areas, including biology, neuroscience, quantum physics, brain medicine, and public health. He is a recipient of the NSF Career Award in 2008 and the AFOSR Young Investigator Award in 2010. He is currently an associate editor of the SciEm Journal on Control and Optimization and the IEEE Transactions on Control System Technology. His talk today will be on control of inhomogeneous dynamics ensembles. Without further ado, let's welcome Professor Li.
Okay, thank you very much for the kind introduction, Struan. So, hi Peter. So I'm here virtually. Thank you for the invitation. So yeah, of course, I'm very happy to be invited, and I am hoping that this next time I can visit you guys physically in Montreal. Okay, so as I mentioned to Struan today earlier, so I'm trying to use my iPad to manipulate to remote control my slides, and then I mean, hopefully it would go smoothly because this is my first time doing this. Okay, so I'm going to talk about control of inhomogeneous dynamic ensemble systems. Okay, so let me start. Okay, so in past decades, the research in systems science and control engineering paid extensive attention on modeling and control of a single or a small collection of systems. And the typical control task is actually to steer a system from an initial state to a desired target state, right? But in recent years, emergent systems, for example, brain and social networks of tremendous scale are prevalent in nature and human society. And these complex systems often, or networks are often constituted by a large number of structurally identical or structurally similar dynamical units. Therefore, research was shifted towards analyzing and controlling collective behavior and dynamic structures of such population systems. So here are some widely observed population systems, neuronal networks, cellular populations, group animals, robust swarms, wind farms, and social networks, where in these systems consist of a population or an ensemble of identical systems or almost identical systems, right? And in many application domains, control and observation of such population systems can only be implemented at the population level. For example, I mean, as you can see, through broadcasting an input signal that has to work for all of the systems in the population. So meaning all of the systems are receiving the same global signal, or through collecting aggregated system level measurements of the population, right? So as you can see, so when the population system is evolving over time, the type of measurements that we can make would be this kind of aggregated system level measurements, like snapshot measurements. And so here I'm gonna show you a couple of prominent applications. So in quantum control, so designing an external magnetic field to excite a large spin ensemble is a fundamental step that enables all applications in nuclear magnetic resonance spectroscopy and imaging. And this control task is actually a key towards unfolding or determination of protein structures and for medical diagnosis. And in brain stimulation, affecting thousands of neurons in the brain by 1 or 2 electrodes is the state-of-the-art technology for neurological treatment of Parkinson's disease. And this is called the deep brain stimulation technique. So, and this is actually just a surgical treatment involving the implantation of brain pacemaker. Okay, and there are many other applications in the domain of robotics and in mechanical systems, right, involving sensorless manipulation of a population of structurally identical dynamical systems. Okay. And so when aggregated measurements are available to us, and is it possible to utilize this type of data to facilitate control analysis and design? So for example, if we look at this video, so we consider a population of spiking neurons, right? So initially, the spiking, I mean, they do not have any spiking patterns, right? And over time, if we are able to collect such aggregated spiking activity, if this can be recorded, right? So, and then we wanted to ask the following questions. Is it possible to exploit such aggregated measurements to design robust inputs to induce desired spiking patterns, as you can see, right? So initially they are spiking randomly, and can we design an input so that we can form specific spiking patterns? Or is it possible to unlock the dynamics of the ensemble and to close the loop in the ensemble system? Okay, so these are major and challenging questions that we wanted to address. Okay, so the grand challenges in control of ensemble systems are actually due to the underactuated nature. So meaning we only have a single or a very few control signals, but we have to manipulate a huge number of systems. And this, I mean, the population could be finite and could be infinite, right? It could be a continuum of systems. And this system, this ensemble system has to be actuated by a global open loops input, right? And if we were able to collect measurements, right? So this is still a lack of step feedback for each individual system, because if we were to measure each individual system, that will require too many sensors, right? And also due to this particular type of aggregated measurements, the control of ensemble systems is actually very challenging. Okay, and okay, so these are the goals of my presentation today. So I will first introduce the notion and formulation of ensemble control systems and problems. And I will present some state-of-the-art methods for ensemble control analysis and design, including controllability analysis and optimal ensemble control synthesis and computation. Then I will show some the applicability and robustness of these methods with numerical and real experimental results in diverse applications. And finally, I will touch upon, I mean, our recent developments in moment-based methods for ensemble control. Okay. Okay, so let me motivate the idea of ensemble control using this very simple example of controlling harmonic oscillators. Okay, so now if we look at this harmonic oscillator, this is actually just a single linear system, time invariant, right? And let me try to see whether I can use my pointer. Okay, and then this system is actually linear. And say if we wanted to steer this linear system from this initial state to this target state at certain time t, right? And it's very easy to see that this system is controllable. This is just a two-dimensional system. And then we can even write down a minimal energy control law steering the system between these 2 points, right? In a closed form that can be done, okay? And so now if we consider an ensemble of such harmonic oscillators, right? So with different frequencies, okay? So omega 1, omega 2, up to omega k. Okay, so then we can put this ensemble into this big system, right? Okay, so now if the number of the system k goes to infinity, and this becomes an infinite dimensional system, right? So is this ensemble system still controllable? and how to analyze this, right? And also how to construct an optimal control law, right? So these are the basic fundamental questions that we wanted to ask. Okay, and formally, so we can actually formulate an ensemble system in this fashion, right? So we consider a dynamic unit, right? So it's called X1. And X1 follows this dynamic law F, right? And then beta 1 is the parameter, the system parameter, right? So for example, it could be the frequency, right? And then we take another one following the same law F, but this one has a parameter beta 2, right? And then we take n of this, right? So this is a small population. So now if n goes to infinity, then mathematically we can actually write this as a parameterized family of systems indexed by this parameter beta and controlled by the same input u of t, right? So anyway, so this is a parameterized family of dynamical systems, right? And so instead of the classical control where we wanted to steer the system from a point to a point, right? So now we are manipulating functions, right? So I mean, in some sense, right? So steering an ensemble system is to steer this system from an initial function to a target function. Okay, and then of course the function space, the state space would be a function space, right? Okay, and then the ability to understand an ensemble system to control such a population system is related to ensemble controllability, right? And then we say that, so if we consider this ensemble system again, so parameterized by this value beta, and usually beta is lying over a compact set, right? And the entire family is controlled by the same input u of t. Okay, and we say that this system is controllable, ensemble controllable, if there exists a control law that will steer the system from an initial function to a desired neighborhood of a target function. So this is just a generalization of the classical controllability notion, right? And ensemble controllability can be defined with respect to different with respect to underlying topology, right? So for example, we can define uniform ensemble controllability measured by if we use the sup norm, right? And then if the distance is measured by the LP norm, and then we can define LP ensemble controllability. So this is anyway, so this is the notion of approximate controllability, okay? And so as you can imagine, so ensemble control problems are unconventional, right? And analyzing controllability requires developing new methods. So here I'm gonna show you the idea of mapping controllability analysis to a problem of polynomial approximation, okay? So here's the idea. So if we, again, so if we consider this very simple linear system, xi equal to x plus bu, and of course, the controllability gradient is just this common matrix BA squared B, and it's very, I mean, we all know this, right? So the system is controllable if the range of W is Rn, and then we say that the system is controllable on Rn, right? So now if we take this ensemble system, right, and this is again, this is time invariant, right? So this is A of beta, B of beta, and A and B are n by n matrix valued continuous function over K, so that actually the state space is actually this continuous function space, right? So the space of continuous function n tuple continuous function over K. Okay, so anyway, so now if we do the same thing, right? So if we take BA squared B, right? And then this set L will never be closed, right? Because actually we do not have Kelly Hamilton, right? Because the power will be raised, and then these terms will go on, right? And so this is anyways, this is an infinite dimensional matrix, right? So now if we write this out, so the reachable set is actually the span, the linear span of this L set, right? And then you can see that it looks like this polynomial form, okay? And And we can say that, so now if this reachable set of this form is dense in this function space, then we can say that this system is controllable over this function space, this state space CKRN, right? Okay, so let me elaborate this by using two examples, okay? So now if we look at this very simple example, this is just a scalar case, right? So we have x star equal to beta x times u, where beta belongs to a compact set K, right? Okay, so in this case, the drift term is actually beta x, right? And this L set after doing BA square B will be 1 beta beta square, right? And then the reachable set is again this the span of this, and that is a linear, a span of this, right? So now we have two things to consider. So the first thing is that the state that can be reached would be lying in this reachable set that can be written as a linear combination of these elements, right? So the state that can be reached would be like a polynomial in beta, right? And the state to be reached would be any function in this function space, any continuous function over K, right? Okay, so then according to the Weierstrass theorem, any continuous function can be approximated by a polynomial arbitrarily well, right? So this is the idea, right? So given this function xi, and we can actually approximate this function by using this polynomial eta, right? So then we can show that for this particular linear ensemble system, this reachable set is dense in this CKR, right? So then we say that this system is uniformly ensemble controllable. Okay. And if we look at the second example, now if we modify the drift term from beta x to beta squared times x, right? And again, we can do BA squared B, we get L, and we can see that this set only contains even orders of beta, right? So in this case, the reachable set contains even, polynomials of even orders, right? And we know that we cannot use an even order polynomial to approximate an odd function, right? So then this system is not controllable. Okay, so this is just denote the idea of polynomial approximation. And so now if we move on to this slightly more complicated case, if we consider a bilinear system, right? And especially this is a bilinear system defined on the Lie group SO3. And so here, epsilon is the parameter that varies in this range, right? So this is the interval of epsilon, right? And we consider this population characterized by epsilon, right? And then we can write this system into, just put this into this form where omega y and omega x are generators of rotation around y and x axis, right? So anyway, so now we consider this bilinear system where epsilon is the parameter variation, okay? So now we have control vector fields, epsilon omega y, right? We also have epsilon omega x, right? So now if you are familiar with nonlinear or geometric control theory, so now in order to understand controllability, we can apply successive Lie bracketing, right? Okay, so if we do Lie bracket of these two vector fields, we will get this one. And the important thing to notice is that we actually raise the power of epsilon to 2, right? So now if we do another Lie bracket, right? If we take epsilon omega y with this one, and then we will raise the power to the third order, right? And we can continue doing this. So we just keep computing Lie brackets, and again, so this will never be closed, right? You can continue doing this because the power of epsilon is actually raising, right? And so now we can collect terms. So we have, so now if we collect terms in omega x, right? So we have epsilon omega x, and we also have epsilon cube omega x, right? And basically we can collect all of the odd orders of epsilon in epsilon of omega x, right? And so now if we use all of these elements as generators, and we can produce the evolution of this form, this exponential form, right? So that is the reachable set actually, right? And then we can use this to approximate any, on the right-hand side, theta of epsilon times omega x, right? So that means that the epsilon dependent rotation around x-axis, right? So anyway, so by doing this successive lip bracketing and collecting all of these elements, we are able to, again, turn this into a polynomial approximation problem, right? So now if this polynomial, right, if this polynomial can be used to approximate this given function, then the system is controllable, right? So anyway, so let me show you, actually I skipped that. So any questions so far? Sorry, so let me come back. Okay, so this is the technique of mapping ensemble controllability analysis to polynomial approximation. Okay, and how about control design, right? So can we compute optimal ensemble control laws for an ensemble system, right? Okay, so to share some ideas, so that's again, so let's just look at this linear ensemble system. So this is a time-varying linear ensemble system, right? And then say we wanted to steer this system from x0 to xf, right? And say that we wanted to find a minimal energy control that will complete this job, okay? Okay, and we know that it's very easy to write down the solution to this system. So this is a solution and by the variation of constant formula, right? And then we wish to steer the system at time t to this final state, right? And after some manipulation, we can see that this solution, the solution to this linear ensemble system, the dynamics is actually characterized by this integral equation. And this is a Fredholm integral equation of the first kind, right? So this is very similar to the classical one, while everything is beta dependent, right? So the right-hand side of beta can be determined by the initial and the target states, where phi is just the transition matrix, right? And the left-hand side is this integral operator, right? Okay, so this system, this linear ensemble system is the dynamics is characterized by this Fredholm equation, right? So now if we were to find the minimum energy control, we are actually trying to solve this optimal control problem involving this Fredholm equation, right? Okay, and then we can show that the minimum norm solution to this problem is of this form. And this is related to the singular system of this operator L, right? So, and then this minimum energy control is actually the infinite sum of the weighted singular function of this operator L, right? And then this infinite series will be convergent, so we can take actually a truncated optimal control, right? So meaning if we wanted to steer the system from an initial state to a very small neighborhood of the target state, the neighborhood is defined by this small epsilon, then the number of terms that we have to truncate will be dependent on epsilon, right? And following this idea, this theoretical result, right? So, and we can actually easily compute an minimum energy control numerically, right? So the idea is actually just to approximate this operator L by using a matrix acting on an appropriate vector of sample values of U, right? And then we can do singular value decomposition. That's it. So computing this can be just done by using singular value decomposition. And this is actually one of my favorite results that I like to show to you. So now if we consider this again, this ensemble of harmonic oscillators. And we have the frequency ranging between -10 to 10, okay? And then, so this is an ensemble system controlled by the same input U and V, right? Okay, so let's say if we wanted to, so if this is the initial profile, right? So in this case, we consider like 101 oscillators. So anyway, so this is the initial profile. And this is actually the target pattern that we wanted to switch to, right? Okay, and then following this singular value decomposition idea, we can design this open loop control U and V, right? So as you can see now, so following this U and V, this ensemble system will be, the pattern will be formed, from this star to a maple leaf at this desired time 40, right? So, and this is done by this open loop control U and V, okay? And then we can actually extend this SVD-based computational method for linear ensemble systems to an iterative algorithm for computing optimal controls for nonlinear ensembles. Okay, so here I will focus on the bilinear case, right? So meaning this case. So I will focus on this. So this is an optimal control problem involving a bilinear ensemble system, right? And then this bilinear ensemble system has a lot of practical applications. So it models actually optimal quantum pulse design. It also models optimal control of spiking neurons. Okay, so let's look at this. Okay, so here's the idea. So now we are trying to extend this SVD algorithm to find optimal controls for bilinear systems. And the idea can be best illustrated by considering just a single bilinear system. Okay, so now if we consider this bilinear system, right, and then we can actually write this time-invariant bilinear system as a time-varying linear system. So meaning we can actually rewrite this system into this form, right? So this is actually the term that we will be rewriting. And then we will be solving this resulting linear system iteratively and until this iteration procedure converges, right? So this is an example. So throughout this talk, I will be using this Bloch system, this system evolving on SO3 a lot. Okay, so this is a system on SO3. This is a bilinear system, right? Okay, so now, so as I mentioned, so we can actually rewrite this bilinear system into this form, right? So where here we just write this as B tilde of X of T, right? So we didn't change anything. We just rewrite this into this form, okay? And so now we have this linear time varying form, right? And we wanted to steer the system from here to here, okay? So the idea is that we can write this into an iteration equation, right? So where on the right-hand side, we assume that we know the trajectory of the previous iteration, right? Okay, so the idea is that, so now if we consider this iteration equation, right? And then if we start with an initial trajectory x0, and if x0 is known, and we can plug in x0 into this part, and B tilde of k is also known, right? Okay, so as soon as this is known, and this is a non-linear system, right? And it's very easy to compute the optimal control, right? That will steer the system from here to here. And we can compute U1 because this is basically just a linear system, right? And as soon as we compute U1, we can plug in U1 into the system and we can get the trajectory. And after getting the trajectory, again, we know B tilde, right? And then we can just do this in this iterative manner. And we are hoping that finally this process will be convergent, right? And of course, finally, we can show that this iterative procedure is convergent, right? And the convergence, under some conditions, okay? And the convergent solution is a candidate for the optimal solution of the original bilinear system or bilinear problem, right? And then meaning the convergent solution will satisfy necessary optimality conditions. And basically, when we are doing this, we are basically just solving an LQR at each iteration. Okay, so let me show you some numerical results. Again, so if we consider this system on SO3, right? And we wanted to design this minimal energy control so that the system can be steered from this north pole to this point 100 on the equator, right? Okay, so if we initialize this algorithm from this U and V, and following this iterative procedure, I mean, these are the updates of the U and V. And after actually 14 iterations, I mean, the algorithm is convergent, and these two are the convergent U and V. Right? And then this is actually the following, the trajectory following this U and V. Okay. And of course, we can extend this to the ensemble version. And this is one example. And the reason that I wanted to keep presenting this system on SO3, because this system is actually, in quantum physics, this system is called the Bloch system. So that is a system modeling, I mean, the evolution of a sample of nuclear spins immersed in the magnetic field, right? So this has a lot of applications in the domain of quantum control. Okay, so here we wanted to design this control, global control, U and V, that will steer an ensemble of these Bloch systems with their frequencies ranging from -1 to 1, from the North Pole to 001, right? And actually following these U and V, actually you can see that, I mean, I just plot some sample trajectories, and you can see that all of the systems with their frequencies belonging to this range can be steered from 001 to 100. Okay, so this is called, because the rotation from 001 to 100 is 90 degrees. So this is called a pi/2 pulse. And then this is called a broadband excitation pulse. And this is very important in protein NMR spectroscopy. So this is the experimental result that I wanted to show you. So in collaboration with Harvard Medical School, so we applied our technique to design a broadband pulse for protein NMR spectroscopy. And so this is the interpretation of the result, right? So, I mean, the goal is to design this U and V so that everything, all of the frequencies between this bandwidth -40 to 40 kilohertz will be uniformly excited, right? So that we can get a very good signal very good signal in spectroscopy, right? And then so the black ones are the signals collected by the traditional conventional approach, and this is collected by our approach. And on the right hand side, you can see that these are the 2D spectrum, right? So our optimal pulse has a lot of enhancement in the signals, right? In this 2D spectrum, right? Compared to conventional methods, right? So this is a real cool application to protein NMR spectroscopy. I mean, by starting ensemble control problems, okay? And here I wanted to also show you this another domain where we can apply ensemble control theory too. Okay, so this is controlling synchronization. So I'll just show you very basic results. So we also have studied this ensemble system consisting of N nonlinear oscillators. Okay, and then we consider these phase oscillators called, for example, chromotor oscillators, right? So the idea is that if we have a rhythmic network, right, we have a network of oscillators, and then over time they could be synchronized, right? And then they are modeled by using this phase model where U is the control input, right? And then the idea is that we wanted to design a global waveform so that this global input will be able to manipulate the synchronization behavior in this rhythmic network. Okay, so I'll just show you, if you're interested in some details, I can show you more after my talk. And so here, I just wanted to show you these experimental results. Okay, and then, so this is we consider an array of 20 chemical oscillators in my collaborator's lab, right? And then different colors denote different state variables, meaning different phase, right? Okay, and blue denotes phase 0 and yellow denotes phase pi. Okay, so starting with this initial configuration, we wanted to design a global input so that we can switch this pattern to O, and then to K, and then back to O. Okay, so this is and this is what we did. So now you can see that this current, this control is our design, and then applying this control to these 20 oscillators, we can see this, and these are experimental results. You can see that we were able to switch patterns. Okay, and this control task has a lot of practical implications, right? So this can be used to do information encoding, and this can be used to develop some computing devices, right? And especially for circadian systems and for brain networks. Okay, I just wanted to show this to you. Okay, any questions so far? Okay, so finally, I wanted to present this moment-based approach that we recently did that I found very, very interesting. Okay. Okay, so far, so I have presented the control of ensemble systems using open loop strategies, right? So where no observations were available or utilized, right? So as we mentioned earlier, that in many applications involving population systems, aggregated type of measurements can be obtained, right? And again, so for the applications that I mentioned previously, especially those applications in the quantum domain, right? So even collecting aggregated measurements is almost impossible, right? Because if you consider a spin ensemble in AMR spectroscopy and imaging, actually the number of spins is only Avogadro's number. It's 10 to the 23rd, right? So having any measurements for individual spin system is impossible. While in many applications, having aggregated type of measurements, for example, snapshot measurements, images would be very possible, right? So when such measurement data, aggregated measurement data become available, how can we properly exploit them to facilitate and enable ensemble control synthesis or ensemble control analysis and design, right? And can we unlock and learn the dynamics of ensemble systems with unknown system models using aggregated data, right? And can we close the loop in the ensemble system, right? So these are the three major questions that we wanted to answer given aggregated measurements, okay? And again, so coming back to this pattern formation, right? So I mean, earlier we have seen that if we consider a harmonic oscillator ensemble, right? And then we can design an open loop law that will steer this system, this ensemble, I mean, from this pattern to that pattern, right? And so now if we can collect aggregated measurements, right? And can we utilize these snapshot measurements to improve our control design and to close the loop in the ensemble system, okay? And so the main idea, so I will be presenting a method that we call moment-based method for ensemble control. I mean, using aggregated measurement, right? So the main idea behind this moment-based method is that when aggregated measurements are available for an ensemble system, and we may endow a probabilistic interpretation of the ensemble system. through these aggregated measurements, right? So namely, we can view the ensemble system as a stochastic process, right? And these aggregated measurements are realizations of this process. So roughly speaking, I mean, we can do this, okay? And so such snapshot measurements can be characterized or can be categorized into two classes, right? So systems with labels and systems without labels. So in the label case, right, so we have these snapshot measurements, right? And so, for example, if we pick up this system, and after some time, we still can identify this system, right, after TK, right? Because, I mean, in this case, those systems have labels, right? And we can track where the systems are. And another case is that we might have systems without labels, right? Again, it's obvious, right? So if this agent is here, right, and after some time t, I mean, if we take another picture, and it would be super difficult for us to know where it is, right? Because they look identical, right? Okay, so now let me just focus on the first case where the systems have labels. Okay, so following the introduced this probabilistic point of view, right? So we can define the moments associated with the ensemble system using its aggregated measurements, right? So now if we consider the systems with labels, right, and we can define this moment mk. So this is the kth moment, right? So in this definition, it looks exactly like the statistical moments, right? So in this case, we do need to know the label because this beta corresponds to this beta in X, right? So when systems have labels, we can define these moments called ensemble moments, right? And where K is a multi-index, right? So for example, I mean, if we consider an ensemble of two parameters, right, beta 1 and beta 2, right? And the second moment has three terms, right? So we have beta 1 square, beta 1 times beta 2, and beta 2 square, right? So these are the multi-indices, right? Okay, just some definition. And so now with this definition of moments, we can further derive the moment dynamics, right, for an ensemble system. Right, so to illustrate the idea, so let's again consider this Bloch system, right? So this is an ensemble system. Where beta is a parameter, right? So this system is of this form. And given this system, right, so assuming that we have this model, and then we can write down the dynamics for the moments, right? So we by taking the time derivative of mk, right? So if we do this, and then for this particular system, this is what we got. And then we can see that on the right-hand side, this becomes actually the k+1th moment, right? So in this particular system, we can see that the kth moment, the dynamics of the kth moment depends on the k+1th moment, right? So this is just the particular structure of this system, which is quite interesting, okay? So now this shows that given an ensemble system, we may find its corresponding moment system, right? Does the reversal hold true, right? So meaning, given a moment system, is there a unique ensemble system determined by this moment system, right? So this is a very, very important question, right? So if we started with an ensemble system, and of course, I mean, we can derive the moment system by defining the moments in this way, right? And we wanted to ask a reversal question that whether given any moment system, I mean, we can use that to determine an ensemble system, right? Okay, and this is actually related to the moment problem in probability theory. Okay, so the moment problem, the classical moment problem in probability theory studies the problem when probability distribution can be uniquely determined by its moment sequence, right? So for example, a Gaussian distribution can be uniquely determined by its moments, right? And so for example, there are various moment problems that people have studied, mathematicians have studied. So for example, the Hausdorff moment problem asks the necessary and sufficient condition that a given sequence be the sequence of moments of some Borel measure supported on a closed interval, right? So in particular, actually, Hausdorff shows that any function f, right, any function f, for example, I mean, in the LP space, when p is greater or equal to 2, has a unique representation, has a sequence that uniquely determines this function. So this is a one-to-one correspondence, right? So given a function, we can find the, given an LP function, there exists a unique infinite sequence that represents this function. Okay, so this one-to-one correspondence is actually forms the key for our development, right? Okay, so here's the connection. So now if we look at this ensemble system, right? And so for the moment, let's consider this system, the state space is L infinity, right? And actually it can work for LP, it doesn't matter. Okay, so now this is our definition of the moments, right? And Hausdorff basically tells us that, okay, so if we consider this ensemble system over this function space where the ensemble state, each state is actually a function in L infinity, right? So the state space has a corresponding moment space, and each function in L infinity, meaning each ensemble state, has a corresponding moment sequence, right? So this is actually the results by Hausdorff, okay? And so this is what we can do, right? So now, can we leverage this result to study dynamics, right? So now this one-to-one correspondence between an ensemble state and its moment sequence allows us to build the connection between the ensemble dynamics and the moment dynamics, right? Okay, so when this ensemble system is evolving over time, right? And we can associate each point, right? We can associate each point, each snapshot measurement, a point on the moment space, right? Like this. And then if we define, so, okay, so anyway, so in this case, right, so on the left-hand side, right, so each point, so this is the evolution of the system, right? And now we can collect aggregated measurements, right? We can have this snapshot measurement. So for each measurement, we can associate these, because we can compute all of the moments, right? We can associate this with a point in this moment space, right? So that this snapshot can have a unique representation of this moment sequence in M, right? And then now if we define this moment transformation, right? So we have L infinity space, and then we apply this moment transformation, right? And then this is actually a one-to-one correspondence, right? And then we can, by Hausdorff, the flow on the moment space, meaning the moment dynamics, right, can then be defined just by the push forward map of L, right? So this is the idea, right? So let me repeat this. So we have two things, right? We have the ensemble system defined here, right? And then we can define moments, right, in the way that we have defined. And now if we can collect these snapshots, right, and we can associate each snapshot a point in this moment space, right? This is by Hausdorff, right? This is one-to-one. Okay, so now if we, and we can actually consider the evolution, the flow of these points, right? So the flow is basically just the push forward of L, right, from here to here, right? And then, and we can easily show that this push forward map is a diffeomorphism, right? So that's not hard to show that. Okay, so specifically, if we consider a control-affine ensemble system, it is straightforward to derive its moment system and see that the moment system is also a control-affine form, right? So now if we consider this control-affine system, and by applying DDTM, right? So now if we compute this, and then this is basically just a push-forward map, and then we can obtain this form. So this is actually also in the control-affine form. So this concludes that if we have a control-affine ensemble system, and its moment system will also be in a control-affine form. Okay, so this is good. This is very good for our analysis. And okay, so again, so this is just a revisit of this bilinear case, this Bloch system, right? So using this language of push forward, right? So we can just given this Bloch system, right? We can compute DDTM, right? We can write down the moment dynamics, right? And so what's interesting here is that this moment dynamics, this moment system seems to be actually a model reduction of the ensemble system. So for example, so the original ensemble system, this Bloch system is this is an uncountable system, right? So there are uncountably many systems, right, in this Bloch system. And so now after this moment transformation, actually this system represents this chain network. And this chain network consists of countably many nodes, right? So you can, this is just an interesting observation. So this is the original ensemble system, and this is the resulting moment system, right? Okay, and why is this correspondence between ensemble dynamics and the moment dynamics interesting and important and useful? Because then we can do control over the moment systems, right? So the established equivalence between the ensemble system and its moment system enables the control of an ensemble system through the control of its moment system, right? And this is actually so far for the labeled case, right? Okay, so this is actually just a summary of what we have done so far, right? So now the idea is that if we have a control-affine ensemble system, right, then we can actually derive the corresponding moment system to this original ensemble system, right? And because there's a one-to-one correspondence, right? So the control of these can actually be completed by the control of these. And this is very, very important for the data-driven perspective, right? So for example, I mean, in many cases, we do not actually need to know the system dynamics of the original system, right? We do not even have the model, right? But we have aggregated measurements, right? So now if we have the aggregated measurements, and then we can actually create a moment system, and we can study the moment dynamics, and we can study the control of the moment system. And that control of the moment system will be working on the original system, right? So that's the best part of it. And furthermore, we can show that so they share the same controllability property, right? So again, due to this one-to-one correspondence, this guarantees that if the original system is ensemble controllable on its own space, then the resulting moment system will also be controllable on its moment space, right? So there is a controllability, the controllability property is preserved under this moment transformation, right? Okay, and so this is actually the data-driven ensemble control framework that I actually just mentioned. So this is what we proposed recently, that how we can use the moment-based approach to develop a purely data-driven ensemble control architecture, right? Okay, so again, so now if we have a system, right, and in general, we might not know the system dynamics, right? So we do not have a model, right? But we can collect all of these aggregated measurements, right? Okay, so we have the measurements, and then we can compute simple moments, right? And then we can, of course, I mean, we might have to assume that the original system is of this control-affine form, right? And then we can try to use these moments and the data to learn the moment system, right? So we can use this to learn F and G, and this is the moment system, okay? And then as soon as this moment system is learned, we can implement, we can execute control design over this moment system, right? And usually we will consider a truncated moment system for control design, right? And then this control design will be moment dependent, and this will be fed back to the original system to close the loop, right? So this is actually the data-driven, the purely data-driven ensemble control framework based on the moment-based approach, okay? Okay, so finally, I just wanted to show you this, I'm just on time. So I wanted to show you this example again. So this is the control of harmonic oscillators. And we wanted to switch the pattern from here to here while using the aggregated measurements to design our control, right? And then you can see that, so we assume that we can observe these snapshot measurements, and then we just apply the control design is just based on the linear combination of moments, right? So we just use 14 moments and to design the control, and this can be done. And this is actually just a very rough simulation so far. So we are trying to refine this, but you got the idea. Okay. Okay, concluding remarks. So my goal is to show you this new and rising area in ensemble control that has many interesting problems theoretically and computationally and practically, right? To study, so controlling collective behavior and engineering dynamic patterns of a population system is a compelling task in diverse areas at different scales, right? You have seen at the scale of quantum, the scale of biology, actually, you see biology, and then actually this can be related to social networks. Okay, and there are many open problems remaining unsolved in both theoretical and computational aspects of ensemble control. And this requires creating advanced and innovative unconventional techniques. For example, studying controllability is actually related to the theory of polynomial approximation. That is not necessarily very trivial, okay? And data-driven methods for inference and control of ensemble and network systems offer a lot of opportunities for systems and control to make significant impact on broad areas, including biology, neuroscience, brain medicine, and topological data science. Okay. Okay, so this is all I want to say. And then these are my students and my postdoctors involving in the works that I presented today and my collaborators. And this is our the only interesting spot in St. Louis that is well known to you, perhaps. Okay, I'm done, and thank you for your patience, and thank you for listening to me, and I would be happy to answer any questions.
Thank you, Jishin, for the very interesting and wonderful talk.